All right, we're going to do summaries from the three discussion groups here, so about 5 minutes per group. So whoever the discussion lead was is going to come down and lead that. You went? Or whoever the group did, that's right. If you have somebody else appointed for the report. So we're going to start with Tim, I think, for the documentation efficiency. Can we go back up? Yeah.
Back up!
Sorry.
Are we trying to go down?
He's doing it. He's getting it. Cool. And just a reminder that we're going to start the process again for the discussion groups tomorrow. So start writing ideas and direct ideas and initials on the board again for the discussion tomorrow and voting as we did for today.
All right, so the question we were given by an anonymous board writer was galactic versus extragalactic star formation efficiency traces. So this is something that is always a big difference when you go to a conference like this that spans scales. If we talk about the word star formation efficiency, it can mean very different things to different people. So we had a discussion at the beginning about what we mean by this. So galactic people studying this will often say this is the mass of young stars, usually measured using YSO counts, over the total mass, so the mass of the stars in that region and the mass of the gas in that region. And so that's what they would call a star formation efficiency, but this would be some YSO count, taking into account the ages, age distributions, etc. here. Whereas on the extragalactic side, typically what we do is we measure a star formation rate in a region, we divide that by the gas mass in that region, and we say, okay, that's how efficiently we're forming gas into stars. And we measure those using some combination of traces that are sensitive to star formation on different timescales. Just like the YSOs are tracing something on a given timescale, all of these trace star formation on a different timescale, but they're all typically much longer than the YSO timescale, which is a big difference. This is important because, at least extragalactically, we see a big variation in this type of quantity between galaxies, and in some cases within galaxies, though typically more between galaxies than within. And so you end up with Schmidt relationships that have very different slopes and normalizations depending on the galaxy that you're looking at. We want to understand the physics behind that, but linking it to this quantity is not necessarily easy because of the differences in how everything is put together. And so how we bridge this gap was what we were trying to discuss. Obviously, it's a hard question, otherwise we wouldn't be able to discuss it. It would have been solved 30 years ago. There's big issues involved. So the filling factor of emission you get when you're looking extragalactically, the temporal resolution of all these traces, and what timescales actually matter for the problem that you're trying to solve. And this is without the fact that star formation efficiency to a galaxy simulator or a cosmologist means something very different. It's the amount of stars you put into your galaxy. So this is constraining the ISM type of definition. So I think the main conclusion we came to is that, at least in the Magellanic Clouds and the local group, this is somewhere where we might actually be able to put these two approaches together to work out what's going on. This was done a little bit in the Magellanic Clouds or in M31, and it was found that those didn't really agree with one another. And so it seems like there's a lot of work to be done there to work out what is going on. How do we convert between these two things in a way that makes sense and allows us to draw from the physics that we can study a very high angular resolution in the Milky Way to the extragalactic way we can study a much greater variety of sources of different environments, but want to get to the same physics. So I don't think we have any conclusions as such. We restate the problem and we at least identify a regime where we can do both and try that out. So I guess that's if I forget anything, people know again.
Cool. Thanks, Tim. Let's do, yes, simulations and observation comparison next. So whoever was leading that, Mordecai, great. And I think we can do the screen down. Yeah, right? Okay.
Doesn't matter. I'm just going to talk. I have no visual aids. Didn't have that. First of all, thanks to Emma for taking notes on this, which I will try to use. So we approached this question by first splitting it up into scales: galactic, extragalactic, ISM, and single regions, whether they be photodissociation, H2, star forming, but regions. And I think the meta comment was observers can't backward model from their observations, but simulators can forward model their simulations to produce simulated observables. Oh, and we can put it in time history, try to understand where things come from and where they're going. Thus, observers are relying on simulators to set their stage. That said, it quickly became clear in the discussion that there's a gap, and that gap can be summed up as radiative transfer, whether it's reducing the emission or convolving it with an instrumental response function and a filter, or converting it from an HDF file of dense temperatures to a FITS file of observable counts in a wavelength, whether that be spectral or spatial. There is a large gap, and frankly, that gap is almost a field in itself. And I think that's really what observers need to understand about simulators, is that interface is one where we're both going to have to contribute and collaborate, because typically, unless a simulation group has unusual resources available, they're not going to be able to generate a wide variety of simulated observations without demand and resources coming from the observational side. Then we discuss specifics. Because there isn't a general pipeline, and because we're talking about very large data sets, really both on the simulation and observation side, but particularly simulations where a time history can be hundreds of terabytes. And that's hard to just transfer around easily, even if you have all the will to make it available. And a few groups have managed to do that. But better to focus in on something and then develop the physics to go from a pure simulation to an observable. Then we actually went down towards smaller scales and realized that the simulations aren't necessarily ready for some of the problems that are being asked, like three-dimensional structure of a photodissociation region. Sounds simple, but requires multiband radiative transfer and three-dimensional MHD. How many minutes do I have left? 0, 1, 2. Okay, 2. Okay. For example, what was the other one that was really nasty? Oh, yes, turbulence. Getting pulsar scattering and quasar scattering measurements down to hundreds to thousands of kilometers, which is completely off the bottom of MHD simulations, requires kinetic particle models that then have to connect seamlessly into MHD simulation parsec scale. That is an incredible modeling challenge, much less than running lines of sight through those models long enough to tell you how a point source is going to vary when simulated over, a kiloparsec or tens of kiloparsecs. So the observers are also pushing the simulators to entirely new ranges of models. Because, we have kinetic models, but, they might be in a box 10,000 kilometers on a side, and everybody would be really excited about how big a box that was, much less connect that to parsec scales. And, there are intermediate hybrid models and so forth, but this is a real scale challenge. And then we also talked about catalogs and deriving data from simulations, things like cluster catalogs or star counts, things that you can have reduced data where you're not trying to do morphology on a FITS file compared to a simulated observation of a FITS file, which is kind of the maximal approach. But if you can reduce both the simulations and the observations, that can be another interface where we can make progress. I think I got most of what we talked about.
Perfect. Okay, and now the reporter for the 3D dust map.
Okay, another anonymous person, I'm not going to say who it was, wrote down how cool it would be if you were to convert the 3D dust mass maps that we already have of the Milky Way also into 3D metallicity maps, mostly because I'm from the extragalactic studies where everything is 2D, and you see a lot of different ionization regions. We're now using cloudy, which assumes 2D spherical models. But as we have already seen from work that Bob Benjamin has showed in his presentation, that the spherical assumption is not really working. So it would be cool, at least from my point of view, from the extragalactic point of view, maybe we can create something where we can convert the 2D information that we have into 3D information using information we have from the Milky Way. So that is, from what I've heard, is already being done. So I'm very happy where the information and the maps that are created from Bob Benjamin's work and other collaborators, so converting using different lines, identifying the H2 regions, and then looking from the different side lines how that flattens out into a 2D H2 region structure, and then you can convert more or less the origin of the different ionizations into the 3D structure in general. So from there, that was the short part. We also extended from the part through, maybe we can use different things with the 3D dust mass maps. So one thing is something that Theo suggested, is that we not only limit us to the ionization, but also use that absorption and emission features in the UV, where you can then compare the different velocity and the distances so that you can easily match it. But then we come into the problem that we need a lot of UV spectra, and we do not have an instrument yet where it is reliable, and a lot of the lines that we want to use are not reliable, such as the calcium lines. Another idea was to try and maybe find cats, but that is mostly as a joke. Dust mass maps. And then finally, we also extended by not specifically looking at how the metallicity then relates to the dust map maps, but then trying to see if we can find spectral features that are dust related using the 3D map, which Craig also showcased in his presentation, where you have different lines related to the far infrared end. Then maybe we can actually use the modeling for that end combined with the metallicity to see whether the features that we see in the far infrared end are related to the different types of dust grains that we can constrain from the metallicity. And that's it. Thank you.
Thanks again to our discussion leads and reporters. You guys did a great job.
Remember to continue putting discussion ideas on the board. We're now going to do some poster flash talks. The screen focus.
Yeah, we need the screen. Now here it comes.
Oh, it's Adam's job right now. Oh, Steve's doing your oh, yeah. Cool.
Yeah, just doing things.
I can do it.
Yep.
All right. Okay, we've got our afternoon poster flash talks, 4 of them. So take it away.
Hi, everybody. First, thanks to the organizers for this really nice conference, and thank you for having me. My name is Vianey Camacho. I'm a postdoc at the National Taiwan Normal University in Taipei. My poster is physical poster number 2 right there. In there, I show the results I've obtained with this incredible team about how massive stars are dynamically heated in turbulent numerical simulations. So the idea in this work is to study how young stellar clusters, how massive stars in young stellar clusters why they exhibit an increase in velocity dispersion when separated by beam of mass, and to study if that characteristic can give us some insights about the dynamic state of the clouds where these stars were formed. So, are the clouds in a state of turbulence supporting or gravitational collapse? Well, come to my poster and I will tell you what we found.
Perfect. Thanks. Where am I? There we go. Who's next? This one? Cool. Great.
Okay, cool. Oh, yeah, right. Hi, everyone. My name is Shanak, and I'm a soon-to-be final year graduate student at Princeton, working with Evo Stryker, Chris Hamilton, and Scott Tremaine, kind of on the intersection of stellar and gas dynamics. So today I want to tell you about some of my thesis work on characterizing ISM fluctuations. And when I say fluctuations, what I mean are these over and under densities you're seeing here in the Tigris simulation suite, which is a state-of-the-art MHD simulation, including self-consistent star formation and feedback and ray tracing and all sorts of cool physics. So these fluctuations are responsible for scattering stellar orbits, producing things like the age-velocity dispersion relation and radial migration, and they also form the birthplace of stars. So what we've done is characterize them by measuring their PDFs and power spectra, among other statistics that I won't have time to talk about, like their spatiotemporal structure and also the vertical structure. And there's lots of applications here, ranging from comparing to observations, such as the surface density maps in FANG's data. And I'm working on the stellar dynamics side, but I'm also curious to hear any ideas you might have. My poster is over there on the far wall. And I'll just advertise right next to it is an example application where they use these fluctuation maps from Tigris to study astrospheres, which Caleb and Catherine mentioned yesterday. So, thank you.
Perfect. Hi, I'm Steve Goldman. Thank you. I work on AGB stars. It's hard to understand the contribution of AGB stars back to the ISM. They're complicated. There's unknowns from differences in age, metallicity, dust properties, geometry. We almost always assume that these stars have spherically symmetric geometries. Now, what we did is we targeted 21 AGB stars that were particularly reddened towards the galactic bulge, and we get deep silicon absorption, crystal absorption. When we combine that with the pulsation data and the maser data, we're pretty convinced that all of them are not spherically symmetric. They have dusty toruses or disks. Also, with that in mind, we can explain that pulsation sequence D on the right-hand side there with these, which has remained a mystery for a couple decades now. So if you can spare a moment for AGB stars, come find me in the cafe.
There we go. Okay. Hi, I'm Christy Erba. I'm a postdoc here at Space Telescope. I work with Christy McQuinn's group. This poster is advertising a recent paper examining different analytic methods for addressing inter+Stellar contributions to polarization, particularly within the context of hot massive stars. So if I can borrow from Steve, if you can spare a moment for hot massive stars, please come find me. Anyway, just the environments near O and B type stars can be quite complex. And of course, polarimetry, in particular linear polarimetry, can help us to disentangle the symmetry breaking elements that affect the geometry of circumstellar environments. So of course, ideally we would isolate the stellar signal just by removing the contribution from the interstellar polarization, but that's not always possible. So this paper is exploring different ways to distinguish the stellar signal even when the ISP can't be removed. And that is hopefully laying the groundwork for future UV spectropolarimetric missions or instruments like Polestar, which is a proposed small mission explorer, or Pollux, which, as we heard earlier, is one of the 4th channel HWO proposed instruments. So like I said, if you'd like to learn more, come find me. I've got this bright red hair, so I'm hard to miss. I'd love to talk to you more about this, or you can follow that giant QR code to read the paper. Thanks.
All right. Thanks all. Coffee break. Yes. Right. I just finished a cup. I need another one. Half hour?
Thank you for attending this session. For the benefit of attendees and the facility staff, we ask that you pick up your cups, utensils, dishes, and other trash around you. In addition, the fold-up desks at your seat impedes other attendees and could contribute to injury if someone happens to step into the extended desktop. The desktops might be soiled from food or drink, and your consideration for wiping off the desktop onto a dish or napkin helps us maintain a clean environment. Your attendance is appreciated, and your contributions are important. Thank you so much.
If you want to, we can do it now, just to You're going now that I'm done with the document.
So many presentations.
Like 15 minutes ago.
Okay, pretty good for you.
So this is session
No matter what.
A.
It's 3 months ago. I said, okay, this month. Thing after, well, I have 2 students who, undergraduate students whose theses were due a couple of weeks ago.
Okay, yeah.
But also a bunch of other shit.
Yeah.
Unrelated.
Yeah. And everything takes 4 times longer than you think it should.
Yeah.
It's insane. The kind of stuff, like crop stuff, and especially, and like, it's bad enough when you're doing like postdocs.
Okay, so I was like, sometimes it would be like stupid shit. Well, Institute telling me, here's the link, click on it, fill out this form, and take 5 minutes. You go to the form, first of all, the link won't work. And that's like half an hour. And then you go to the form, but they don't want you to use Firefox. So then I have to go to Safari, but then it still won't work. Like, before I know it, it's 3 hours. It's like half a day wasted.
Okay, do you know which one of these two, Sundar, is your final uploaded one? They both have long numeric.
Let's see. Well, is that the one with the time?
Yeah, that has additional stuff after it on the top.
Yeah,
so
okay.
That one.
I don't know what, because I didn't add that when I saw.
Oh,
that,
okay.
Yeah. So I know which one. Just the last slide. Yeah. How do I?
Okay, I'll just download it.
Sorry, I was hoping you wouldn't have to.
No, sorry, it's come on. Where'd you go?
I changed like a word.
You gotta make things difficult.
I figured it would
Okay,
override.
yeah.
I don't know. Yeah, done.
Perfect. Okay, and then.
I had to say develop a model grid. So.
And then here is yours. And if I.
Can I just make sure like my
Oh, yeah.
dumb animation
Oh, sorry, I already
is
pressed
working?
full screen. Oh, no, I didn't. Okay, cool, yeah.
Yeah. Let me just go to the relevant slide here. So, oh, you gotta actually press the button. Okay, not just tap it.
Takes like 3 seconds to put up there, so.